For our machine learning project, we decided to classify state-backed bots on Twitter. Twitter's at the forefront of social media these days. It's a popular microblogging site where users can share information in real time. Because of this, people use it to check the news and keep up with politics. This has led to many nation-states, however, taking advantage of people's Twitter feeds, where they create Twitter bots, which are also just known as fake accounts, to push out propaganda into the feeds of users all over the world. In fact, Russia allegedly made and controlled thousands of these bots to influence voter opinion in the US 2016 election. As the next US election draws near, we decided we wanted to try and train classifiers that could detect these dangerous entities on Twitter. We approached it as a binary classification problem, where one label meant a tweet was from a bot, while the other meant it originated from a real account. We thought it would be in our best interest to split the problem between regular and textual classification. We didn't want to lose out on what either would offer, so we decided to make models for both approaches. Collecting the data for the fake tweets was easy enough. Twitter releases datasets every month that they suspect originated from nation-state-backed bots, and even groups them by country. We chose to use tweets from China, Iran, and Russia. For the real tweet data, it was a bit more difficult. We had to write a custom Python script using a Twitter API wrapper called TweetPy to parse through tweets and scrape data directly from Twitter's stream. We manually verified that the tweets we collected for our authentic data set were either from verified or unverified yet authentic accounts. An example of such an account would be like an account of yourself or your friend, assuming you weren't verified. From our research, this approach was a bit novel in the way that most researchers that approach this problem only included in their authentic dataset verified accounts. This obviously could lead to some bias, as everyday people kind of don't tweet necessarily the same way as brands and celebrities would tweet. So after collecting the data, we read them from CSV files into Pandas data frames, where we assigned them labels before shuffling them up. We also performed some data exploration, noting interesting trends, like how temporal data for the bot accounts was a lot flatter in its distribution than for the real accounts. We also noticed there was a positive correlation between the number of likes and retweets on a tweet, as well as a negative correlation between the number of likes and the number of URLs and hashtags. The word clouds were also interesting. The words in the bot tweets had a lot of politically charged jargon like Islam and Syria, while the words in the real accounts were a bit on the softer side. We chose models based on our research of the classification problem itself, and as well as models that we had learned about in class. We ended up choosing logistic regression, random forest, and naive Bayes for the text classification portion. We isolated the text data and the respective labels from the tweets before performing the standard NLP procedures on them. This included using regex to strip down unnecessary characters, using the NLTK package to strip stop words from the tweets and lemmontize them. We tokenized the words, and after this passed them into a TF-IDF vectorizer to transform the data into a term frequency matrix, which was what was then fed into our models to train. The TDF scores based not only on how frequent the words appear, but also how unique they are across the whole collection of words, also known as the corpus. We wanted to run our models with the raw data as well as after reducing dimensions. So for the text data, we used truncated SVT to perform this. We used a standard train test split procedure and sklearn to train the models with the data. The results varied, with the raw data of all three models performing similarly. However, with dimension reduction, random forest outshone its peers and would prove the best in a real-life scenario given its ability to be efficient and scalable. For the normal classification, we had a similar pipeline. We extracted 8 useful features and stripped away the rest. We again chose our models based on research in class, including logistic regression, random forest, naive Bayes, gradient boosted decision trees, and SVM for the supervised portion, and k-means and GMM for the unsupervised portion. We chose to use PCA to perform the dimension reduction for this go-around. We reduced the features of 2 components and observed a positive correlation. The results were again varied, and the random forest and gradient boosted decision tree performed the best with PCA. These two would be the best for real-life scenarios because performing well while reduced to 2 components means they're much more scalable. The random forest model was experimented on by tuning its 2 parameters, including the number of estimators and max tree depth. The tree depth proved to have a lot more influence on the accuracy than the number of estimators. So we performed unsupervised learning out of curiosity more than anything else, and the results were predictable, far worse than the supervised models, but 50% accuracy was still respectable from k-means and GMM, seeing how we didn't attempt to favorably tune out our data into 2 clustering models. Overall, this project was a blast, and we learned a lot. We tried to ensure that we were following best practices along the way to the best of our ability to ensure that we were taking on a valid approach and would get valid results. Low accuracies would have implied that we were not able to generate a valid prediction from the features we selected and engineered, and super high accuracies would have implied that maybe we had some error in our methodology and feature selection. It is also worth noting that we use a series of scoring methods and visualizations that we featured in our GitHub page to additionally evaluate our models. The confusion matrices gave a good indication of the percentage of true and false positive predictions our models were making. Overall, this project was very interesting and we were satisfied with our results. With some of our models like the random forest classifier demonstrating a high accuracy in identifying bots, we felt we contributed to the latest efforts in building a safer internet with other data scientists.